Hello YouTube. Today we're going to return to some of the issues concerning confirmation of scientific theories. What counts as good evidence for a theory? Obviously, theories entail observations, and we expect a theory to fit the observations that we make. So if a theory is to be acceptable, obviously the observations we make have to confirm it. They have to match what it predicts. But there are different ways of doing this. So when a theory makes a claim about some piece of data that has not yet been observed, this is known as a novel prediction. When a theory is explicitly designed to explain a set of data that is already known, this is known as an accommodation of the data. And there is a common attitude in philosophy of science that greater confirmation is provided when a theory predicts a new, surprising phenomenon, when it makes a novel prediction, than when it merely accommodates or explains the phenomena that we are already aware of. So there are numerous cases in the history of science that seem to illustrate this. For example, the chemist Mendeleev, he found that on the basis of his periodic table, properties of elements could be predicted from their atomic weights, and he correctly predicted the properties of germanium, gallium, and scandium. The prediction of the properties of these elements was seen as being more powerful evidence for his theory than his accommodation of the properties of the 62 other elements that were then known. So these three predictions outweighed the 62 accommodations. Similarly, Newtonian mechanics gained a great deal of support after its prediction of the return of Halley's Comet. General relativity had the striking prediction of the value of the gravitational deflection of light around the sun. Fresnel's wave theory of light is known for its novel prediction of the Arago spot, which is a bright spot at the centre of a shadow produced by a circular disk. So cases like this seem to show that evidence provides greater confirmation when that evidence is predicted by a theory than when it is merely accommodated by a theory. So what we're going to ask in this video is, how much does novel prediction matter? And we can distinguish, for our purposes, three views here. I guess I should note that the terminology is sometimes used a bit differently, but this is how we're going to divide it up, divide up the conceptual space for the purposes of this video. So strong predictivism claim is the view that evidence confirms a theory only when the evidence is a novel prediction. So accommodation of old evidence has no power to confirm at all, right? In terms of theory evaluation, accommodation of old evidence is useless. It doesn't support a theory at all. Only novel predictions support a theory. Predictivism is the view that, yes, accommodation of old evidence has confirmatory power, but it just doesn't have as much as novel prediction. Other things being equal, novel prediction is better than accommodation. Finally, accommodationism is the view that novel prediction and accommodation are equal. Novel predictions do not have greater power to confirm. All that matters is that the theory entails the correct observations. It doesn't really matter whether those observations, it doesn't matter when those observations have been made, whether they're made in the future or have already been made. So it may be worth noting that there are different types of novelty. So there are different ways of defining what counts as a novel prediction. So it's said that evidence has temporal novelty if the evidence was not known at the time the theory was constructed. And all of the cases that I just noted at the beginning are cases of temporal novelty. The Arago spot, for example, was something that was unexpected when Fresnel developed his theory. Indeed, it was initially seen as a completely absurd result. The fact that Fresnel's theory entailed the Arago spot was taken to be a serious problem for the theory. But then the experiment was performed and the prediction was confirmed. So, that was a clear example of temporal novelty. Nobody expected the Arago spot when Fresnel proposed his theory. On the other hand, evidence has use novelty if the evidence was not used in the construction of the theory, if the theory was not built to fit the evidence. So, temporal novelty is probably the most striking, it's the most surprising, let's say. But I think in terms of confirmation, most predictivists would probably say that use novelty is what matters. So evidence that was not used in the construction of a theory, evidence that the theory was not built to fit, counts in favour of that theory more than evidence that the theory has accommodated. I should also say, for those of you who are familiar with my series on scientific realism, you will probably notice a connection here with the realism-anti-realism debate. The standard argument for realism is that the striking success of our best scientific theories justifies belief that those theories are true. And what kind of success matters? Well, most realists place the emphasis on successful novel predictions. The standard realist view is that those mature scientific theories that have made successful novel predictions, those are the ones that we should believe are true. So, I'm not really going to discuss realism more here, but I just note that one way to challenge a common argument for realism is to deny predictivism, to deny that novel predictions are special. Okay, well, with that said then, let's start with some of the arguments for predictivism. Well, probably the most common argument for predictivism is the no coincidence argument, which is actually very similar to the no miracle argument for scientific realism, though in the literature on predictivism it seems to be called the no coincidence argument, so we'll go with that. So anyway, suppose that some theory T makes a correct novel prediction E. The question is, why was T's prediction correct? Well, the idea is that we can explain T's success here in two ways. So one possibility is that T is true, or at least T is true for the relevant class of observable phenomena. So that would explain why T got E right. The other possible explanation is that T's success here is just a coincidence. There have been cases where false theories have made correct novel predictions. This is just sort of by chance, just by coincidence. Obviously, sometimes theories get it right. A broken clock is right twice a day. So same with the relation between theories and evidence. Sometimes false theories just do make correct novel predictions. But in general, the thought is, we shouldn't suppose that there are such surprising coincidences like this. In most cases, the truth explanation is better than the coincidence explanation. Indeed, the coincidence hypothesis, let's call it, doesn't really seem like an explanation at all. So the idea there is that, well, when T novelly makes a novel prediction, a correct novel prediction E, the best explanation we have for why T's prediction was correct is that T is true. On the other hand, suppose that T is constructed so as to accommodate E. Well then, why does T entail the correct observation? Well, here there's a different explanation for T's success. If T has accommodated E, then we can say that T successfully predicts E because T was specifically designed to predict E. So, we have a design explanation, and obviously this design explanation is not available for novel predictions. So to lay it out visually, we have sort of this situation. We have competing explanations for a successful prediction E. In the case of novel prediction, the possible explanations are, well, either T is true or it's just a coincidence. In the case of accommodation, we have the explanation that T is true and that T was designed. So the point is that with accommodation, we have to accept the design hypothesis because we know that T was designed to entail E. Now, perhaps T is true also, but in this case, the truth of T is totally redundant as an explanation for its successful prediction. Its successful prediction is fully explained by the design hypothesis. The assumption here is that we shouldn't endorse redundant explanations. If some fact is fully explained by a hypothesis and assuming this hypothesis is uncontroversial and accepted by everybody, then we shouldn't introduce some other hypothesis to also explain that fact. And obviously the design hypothesis in this case is, so the argument goes, uncontroversial and accepted by everyone. So in the case of accommodation, the design hypothesis trumps the truth hypothesis. On the other hand, with novel prediction, well, we can't appeal to the design hypothesis. Obviously, T was not designed to entail E. What's more, truth and coincidence are incompatible explanations. I mean, we have to go with one or the other. And truth is, as I said, a better explanation than coincidence. So, is this convincing? Well, Eric Barnes in Neither Truth Nor Empirical Adequacy Explain Novel Success suggests an interesting response. Barnes points out that the design hypothesis concerns the intentions of the theorist. It concerns how the theorist went about constructing their theory. And he then argues that the truth of a theory and the intentions of the theorist explain different things. So it makes no sense to say that the design hypothesis renders the truth hypothesis redundant. The truth of a theory explains why it entails the correct claims about the world, why it entails the observations we actually make. But it can't explain why the theory was chosen, because obviously we can't directly access the truth of a theory. On the other hand, the intentions of the theorist explain why a theory was chosen, but intentions don't explain the consequences of a theory. So we can't claim that this is a better explanation for the accommodative success of a theory than is the truth of a theory. So I think maybe the best way to understand what Barnes's point seems to be is to lay it out like this. We have two scenarios, right? So in the first scenario, let's say that T novelly predicts E. Well, what does this mean? Well, it means first of all that T entails E, second that T was not designed to entail E, and third that E is the case. On the other hand, we have a scenario where T accommodates E, and what this means is that T entails E, T was designed to entail E, and E is the case. Now, remember that the claim of the no coincidence argument is that truth of T explains T's success in the first case, whereas design but not truth explains T's success in the second case. So let's consider these two possible explanations. Let's take first the truth explanation. Well, in both cases, the truth of T is obviously irrelevant to the first conjunct. The fact that T entails E is a logical fact. So the wave theory of light would still entail the Arago spot even if light were not a wave. That's just a logical relation between the theory and what it entails. Also in both cases, obviously the truth of the theory is irrelevant to the second conjunct. The fact that light has wave characteristics doesn't explain why Fresnel did not design the wave theory to entail the Arago spot. Finally, in both cases, the truth of T does explain the final conjunct. So the truth of the wave theory explains why the Arago spot is seen. The truth of T explains why E is the case. And in this sense, it explains why T novelly predicts E, but it also explains why T accommodates E. Okay, so let's consider the design hypothesis. So in both cases, the fact that T was designed to entail E is completely irrelevant to the first conjunct. So that T entails E. The design hypothesis doesn't explain this because the fact that T entails E is a logical fact. T would entail E whether or not it was designed to do so. General relativity would entail a certain value for the precession of Mercury's perihelion, whether or not it was designed to do so. Fresnel's wave theory would entail the Arago spot, whether or not it was designed to do so, and so on. So design doesn't explain the first conjunct. It also doesn't explain the third conjunct. Obviously, the fact that a theory was designed to entail E doesn't explain why E is the case. In the case of the second conjunct, well, in the case of novel prediction, the design hypothesis just contradicts it, right? Because the design hypothesis says that T was designed to entail E. And in the case of accommodation, it just reasserts the second conjunct. The design hypothesis is, that T was designed to entail E, so it doesn't explain that. So the design hypothesis isn't really an explanation for either of these things. And so, again, so it doesn't really make any sense to say that the design hypothesis makes the truth hypothesis redundant. So let's consider a different argument. This argument has been suggested by Patrick Meher in his article Prediction, Accommodation and the Logic of Discovery. And he begins by asking us to consider two scenarios. In the first scenario, Frank is presented with some evidence E, a sequence of 99 coin flips that are apparently random between heads and tails. And Frank is told to provide, let's call it a theory, of the first 100 flips of the coin. Frank responds by citing E, by citing the first 99 coin flips, and then adding a prediction for the 100th flip. And so we'll, again, call this theory T, and so we have something that looks like this, right? So this is, Frank's theory. It's just an apparently random sequence of heads and tails. In the second scenario, Vincent is asked to predict the first 100 flips without seeing any of the flips, and assume that Vincent responds with T. Then the coin is flipped 99 times, and in all 99 cases, Vincent's predictions are correct. So the question is, in which of these scenarios is T better confirmed? Well, surely it's in the second scenario. Surely we would all be far more confident about the prediction of the 100th toss in the second case. We would be far more confident about Vincent's prediction. So in the first case, we would probably say that there's a 50-50 chance that Frank's prediction of the 100th toss is correct. In the second case, we're almost certain that Vincent's prediction is correct, because we think that that Frank is just guessing. The fact that the theory is true for the first 99 tosses is no evidence at all that the prediction of the 100th toss is correct. But in Vincent's case, it seems that he has a reliable method for predicting the outcomes of the tosses. So for Meher, this vividly illustrates the distinction between prediction and accommodation of evidence. A successful prediction confirms the reliability of the method. A successful accommodation does not do so. So yeah, Meher's example does really seem to drive home the appeal of predictivism, but there are responses. Mark Lang, in the article The Apparent Superiority of Prediction to Accommodation as a Side Effect, suggests that the relevant difference between the two cases is not that the first is accommodation and the second a novel prediction, but that the first involves an arbitrary conjunction. So, a theory is an arbitrary conjunction when its claims about various cases seem to be unrelated to each other. So as an example, consider this theory. Protons contain two up quarks and all animals share a common ancestor, and Captain Beefheart was born in 1941. Clearly this isn't really even a theory, is it? We could confirm this conjunction, but only by confirming each conjunct. Nothing ties these conjuncts together. This is completely arbitrary. Naturally, we're only going to propose an arbitrary conjunction like this after the data has already been gathered. This is always going to be something that accommodates the data. So in Meher's example, in the first case, the prediction of the 100th toss is merely tacked on. Frank has no reason, as far as we can tell, to prefer heads over tails. So his theory T forms a completely arbitrary sequence. On the other hand, when T is predicted, as Vincent predicts it, well, it may initially seem like an arbitrary conjunction, like a purely random sequence, but the confirmation of its predictions shows that it isn't. And this is why we trust the prediction of the 100th toss in the second scenario, because we have reason to believe that T is not an arbitrary conjunction. Lang supports this claim about arbitrary conjunctions by imagining an alternative scenario. So imagine that rather than a random sequence of coin flips, we toss the coin and we get a sequence of alternating heads and tails. Heads, tails, heads, tails, heads, tails, heads, tails, etc. Again, in the first case, Frank is shown the sequence of 99 flips and he's asked to predict the outcome of the 100th flip. In the second case, Vincent proposes the alternating sequence before learning of any of the actual outcomes of the flips, and his prediction is shown to be correct for the first 99. In which case do we have greater confidence in the prediction of the 100th flip? Well, Lang says in this case it doesn't seem to make any difference. Obviously the fact that Vincent has predicted this would suggest that Vincent knows something about the coin, whereas Frank might not know, why the sequence is alternating. Vincent perhaps could give more of an explanation than Frank could. But in both cases, we are really very sure that the 100th flip is going to land tails. So this shows that it's not novel prediction that makes the difference. I suspect that what's sort of perhaps misleading about Mayer's thought experiment is that coin flipping is an exemplar of a completely random process. It's an exemplar of something where the outcome really can't be predicted beforehand. So when the predictor correctly predicts the first 99 flips, we want to ask, on what basis was this prediction made? In any realistic scenario, surely such a prediction would have been derived from some background knowledge about the coin. For example, perhaps the coin was flipped by a mechanical arm that could flip precisely enough to ensure heads or tails. And then the run of heads and tails was determined by a computer program written by Vincent. Well, in that case, we understand why Vincent's predictions were accurate. But if the predictions were supported by background knowledge like this, then in the case of accommodation, as long as that appeals to the same background knowledge, we would trust the prediction of the 100th toss just as much. Because in both cases in this scenario, the sequence of flips is not an arbitrary conjunction. There is something that ties the sequence together, that puts people in a position where they could be able to know what the outcomes would be. On the other hand, if we're being asked to imagine a case where Vincent's predictions are all correct, but he can cite no reasons for this, well, in that case, it's very hard to draw any conclusions about scientific theory confirmation from it, because it's just such a bizarre scenario and doesn't really, it's not at all similar to anything that would actually happen in the real world. So it's kind of hard to know how to respond to that. Okay, so a third argument for predictivism appeals to falsifiability. Essentially, the idea is that only novel predictions can be falsified. So I should just note, this argument doesn't necessarily depend on Popper's falsificationism. Indeed, as we saw, Popper denies that we can ever confirm theories. For Popper, neither novel predictions nor old evidence are confirmatory. But Popper did think that more weight should be accorded to novel predictions because these provide severe tests of theories. So recall that for Popper, science involves making bold conjectures that give clear specifications of the conditions under which they would be refuted. So he does think novel predictions are better in some sense than accommodations, even if neither confirm a theory. But anyway, even if we reject the details of Popper's falsificationism, we would probably still think that falsifiability is an important aspect of scientific theory evaluation. In particular, it seems plausible that there is a link between falsifiability and confirmation. A crucial feature of science is that scientists test their theories, but the result of a test can confirm a theory only if that test could also have falsified the theory, only if the test could have had a result that the theory did not predict. In the case of old evidence, the result is already known, so it has no power to falsify. Obviously, the facts fit the theory because the theory was constructed to fit them. The facts had no chance of refuting it. T would be just as likely to accommodate E whether T was true or false. So accommodations have no confirmatory power. They're not really tests in the way that novel predictions are. Indeed, it's worth noting here that accommodation might actually lower a theory's falsifiability. The more evidence that a theory is built to fit, the less there is that can potentially falsify it. So, from this point of view, accommodation might actually be a bad thing in many cases. So how might the accommodationist respond? Well, one possible response is to say that this argument rests on a faulty view of why falsifiability matters. So we want theories to be falsifiable because theories will always confront new data. And in particular, we use theories to form expectations about what we are going to find in the future. We apply theories to, in our dealings with the world. If I want to, send a probe to Pluto or something, then I have to use a theory to tell me what's going to happen with the gravitational interactions between the probe and the planets, and so on. But a theory can only help us form useful expectations about the future if it rules out a host of possible occurrences. The theory needs to tell us what will happen and what will not happen. So, imagine that a theory becomes unfalsifiable. It introduces a number of ad hoc hypotheses to save itself from refutation by new information. Well, the problem then is that the theory will be compatible with too many observations. It wouldn't rule anything out, or it wouldn't rule enough out. So, like general relativity will tell you by exactly how much the clocks on satellites orbiting the Earth will diverge from the clocks here on Earth. It will specify exactly what the difference is going to be, and that specificity is what makes it useful. An unfalsifiable theory wouldn't have that. So we can kind of account for what's important about falsifiability without saying that that this is what is sort of crucial to theory confirmation. Another way to defend accommodationism is to argue that unfalsifiable theories are also unable to properly accommodate data. So the thought here is that for a theory to properly accommodate a piece of evidence, the theory must explain that evidence, and a proper explanation of some phenomenon will rule out alternative scenarios. If you explain everything, you explain nothing. So, again, imagine adding ad hoc hypotheses to general relativity so that it became compatible with various other values for the time difference between clocks on satellites and clocks on the Earth. In that case, it wouldn't really count as an accommodation of the time difference. I mean, if general relativity allowed that the clocks could, diverge by all sorts of different amounts, then it hasn't explained why they diverge by the specific amount that they do. So it hasn't really accommodated that evidence. So in fact, when a theory becomes unfalsifiable, that ends up removing its ability to accommodate evidence as well. Okay, a fourth argument for predictivism appeals to probability theory, in particular Bayesianism. Now, I'm not going to explore the details of Bayesian epistemology here. It can get quite technical, and I intend to examine that in a later video. But the basic idea for our purposes is that E confirms T only if E raises the probability of T. In particular, then, E confirms T when the probability of T given E is greater than the probability of T. So that's what this thing here is saying. So that's the probability of T given E is greater than the probability of T. In Bayesian language, when the posterior probability of the theory is greater than the prior probability of the theory. And I mean, I think the idea here is pretty intuitive. All this really means is that, it just means that as a result of the evidence, we raise the probability that the theory is true. So evidence confirms a theory when, as a result of that evidence, the probability that the theory is true goes up. And Bayes' theorem gives us an algorithm for updating your beliefs based on the evidence. Here's what it looks like. Again, the details aren't really important, but we have the probability of T given E equals the probability of E given T multiplied by the probability of T, and that divided by the probability of E. Now, We can simplify this a bit because much of the time T entails E. So as long as T logically entails E, then obviously the probability of E given T is equal to 1, which reduces the equation to the probability of T given E equals the probability of T divided by the probability of E. So, what's all this got to do with predictivism? Well, if E is a novel prediction, then the probability of E must be less than 1, since it might turn out to be false. In the case of truly surprising predictions, the probability of E might be very low indeed. The probability of E before we do the experiment, before we make the observation, is going to be less than 1. So in which case, when we then find that E is true, that we make the observation and the evidence is confirmed, well, that confirms the theory. But when E is known, when it's already known, when E is an accommodation, then the probability of E is equal to 1, in which case the probability of T given E is just equal to the probability of T, because you can see that from this equation here, if the probability of E is equal to 1, then you just have the probability of T given E equals the probability of T. So the accommodated evidence has no effect at all on your degree of belief in the theory. I mean, I wouldn't, so again, for the purpose of this video, the sort of technical details aren't really so important. I think we can put this in intuitive terms. When we have a theory that accommodates old evidence, well, the evidence is already known to be true, and so it can't function as new information that changes the probability of the theory. So I guess in a way this argument is making the same kind of point as the falsifiability argument in a slightly different way. Because, again, the conclusion of this argument is that a theory can't really be tested by a piece of data that is already known, or a piece of data that it was engineered to entail. Now, I should note that this is often presented as a problem for Bayesianism. It's known as the problem of old evidence. So the accommodationist could just, respond with this standard position that actually, this is really a problem for Bayesianism rather than an argument for predictivism. But we might say, well, look, we do have a nice connection here between two independently plausible ideas, Bayesianism and predictivism. Both of these have found a lot of support among philosophers for different reasons. So since it turns out that Bayesianism seems to entail predictivism, that unifies the ideas rather nicely. So maybe this is another argument you might use for predictivism. Okay, so those were some of the arguments in favour of predictivism. So let's turn then to the arguments for accommodationism. I mean, one point, I guess, to make at the start, which isn't so much an argument, but just a sort of competing intuition. We saw at the beginning of the video that predictivism is supported by various cases in the history of science of successful novel predictions, like Mendeleev's prediction of the properties of just 3 elements seemed to lend greater support to his theory than the accommodation of all the other elements that were known at the time. So, that intuitively seems right. Predictivism has quite a powerful intuition in its favour there. But we do have competing intuitions here. A fundamental claim of predictivism is that the way that a theory was discovered or constructed should have a bearing on whether or not we accept the theory. So what this means is that the occurrence of certain psychological processes in the people who developed the theory could undermine our confidence in the theory. But that seems rather strange. I mean, there's a sense, you sort of think, well, surely, all that matters is just the evidence for the theory. It doesn't matter how the theory was developed, how it was constructed. All that matters is the observations and experiments that we make, whether they support the claims that the theory makes. So philosophers of science have traditionally drawn a distinction between the context of discovery and the context of justification. The thought is that how a theory was developed should be irrelevant to whether or not it's an acceptable theory. Theories can be thought up in dreams. Discovery is non-rational. It's a purely psychological matter. what we're interested in if we're talking about theory confirmation is the context of justification, and how a theory was discovered is irrelevant there. Well, predictivism obviously denies this distinction because it holds that the means of discovery plays a role in justification. Predictivism entails that our support for a scientific theory should decrease, for instance, if our views about the history of its development change. So, when scientists evaluate a theory, should they be concerned about how the theory was constructed? Should they pore through the notebooks of the scientists who developed it to see what data was used in its construction? For example, if it had turned out that Mendeleev had in fact known about germanium, gallium and scandium before proposing his periodic law, would that decrease our confidence in his theory? That seems a bit counterintuitive. So anyway, one popular argument for accommodationism then is the history of science argument. So as I said, at the beginning of this video, we saw a number of cases in the history of science where correct novel prediction led scientists to accept a theory. But accommodationists often claim that this is just false, that scientists don't, in general, put greater weight on novel prediction over accommodation. Stephen G. Brush has done a lot of work examining some of these historical cases, and he's argued that the history doesn't support predictivism, for instance in his article Dynamics of Theory Change. So I just want to briefly note some of Brush's historical findings. So on quantum mechanics, Brush argues that this was accepted before its novel predictions were confirmed, and physicists didn't ascribe greater weight to the experiments that confirmed the novel predictions. Indeed, the novel predictions weren't actually all that important at all. The reason why quantum mechanics was accepted, according to Brush, was because it was such a general and powerful theory, because it accounted for anomalies that had plagued its predecessor theories, and because it provided a single consistent method for performing calculations instead of just a whole collection of ad hoc rules as previous theories had done. On general relativity, Brush finds that the accommodation of the precession of Mercury's perihelion, something which had long been an anomaly for Newtonian mechanics, was considered by scientists to be equally strong evidence as the novel prediction of gravitational light bending. Indeed, if anything, he thinks that the Mercury effect might have been even stronger evidence than light bending. On Mendeleev's periodic law, Brush points out that when the Royal Society awarded the Davy Medal to Mendeleev, it never even cited his successful predictions. Instead, it discussed his achievement in establishing, and I quote, foundations of a general system of classification of the elements, and also, and I quote, the marvellous integrity with which the differences of properties, end quote, of the sequences of elements are reproduced in different rows. So what they seem to be citing there are his accommodations of the elements that were previously known, not his correct predictions of the other few elements. Brush has also found that discussion of the periodic law in chemistry textbooks of the time, again focused almost entirely on the accommodations rather than predictions of new elements. The main reason for the acceptance of the periodic law was how it established a correlation between the properties of elements and their atomic weights. Just as a final example, which isn't cited by Brush, but this is just another example, is possibly Darwinian natural selection and its unification with Mendelian genetics in the early 20th century. This unification of theories, the modern evolutionary synthesis as it's known, is often considered to be one of the most powerful and best confirmed theories in the history of science. Yet novel predictions didn't really play a significant role in either Darwinism or Mendelism or their unification. So I have a video called History of Biology Darwin 1, and from around 20 minutes in I talk a bit about Darwin's methodology. What was striking about Darwinian natural selection was how it captured a broad range of data under a single theory. And then the unification with Mendelian genetics in the early 20th century, what this did is that at one stroke it resolved a number of anomalies for Darwinism, and it also connected together two very powerful theories that had previously been seen as in tension. So it sort of resolved a significant problem for biology at the time. But novel prediction, as far as I know, didn't play such a significant role in the acceptance of modern evolutionary theory. Finally, of course, there are also cases Brush finds where theories made correct novel predictions, but they weren't viewed as well confirmed. So in his article Prediction and Theory Evaluation, Brush discusses a number of correct predictions made by Hans Alfvén's electromagnetic plasma theory of the solar system. This theory, although it made 4 or 5 quite surprising novel predictions, it was never taken all that seriously by other astronomers, presumably because they judged its other explanatory virtues to be too lacking. They judged its prior probability to be too low. So, if you're interested in the history here, I'd recommend checking out Brush's work on predictivism. So, assuming that the historical claims here are correct, is this a convincing argument for accommodationism? Well, one obvious problem here is that this argument involves just examining how scientists have actually behaved. It involves examining under what circumstances scientists have in fact been led to accept or reject a theory. But, the behaviour of scientists may not be ideal. Scientists aren't perfect. They do make mistakes. You can find cases in the history of science where it seems like scientists have accepted a theory on the basis of, rhetoric or prejudice or whatever. That does happen. So we might say, look, scientists should have given greater weight to novel prediction. They should have put more weight on novel prediction, even if they didn't actually do that. Predictivism, after all, it's a sort of normative claim. We're saying that novel prediction is better than accommodation. It provides greater justification, greater confirmation. But then describing the behaviour of actual scientists doesn't really tell us anything about that, or at least so it seems. So the accommodationist, I suppose, might say, well, there is a norm that's respected by most philosophers of science, which is that it's not up to us to say what the appropriate standards of science are. Our claims about the scientific method and about the process of theory confirmation and justification need to fit the behaviour of actual scientists. So one way to approach philosophy of science is to think that scientists are following all kinds of implicit standards, and the job of philosophy of science, at least if we're talking about theory confirmation, is to make those standards explicit, to state explicitly, what the standards of science are for evaluating theories. But we're not trying to change the standards. We're not claiming to be able to improve science. That's not our job, Science doesn't need our help. So from that point of view, if scientists do not lend greater weight to novel prediction, then predictivism is wrong. But of course, that's a controversial matter. You might well say that, well, actually, philosophy of science can kind of go can sort of make reforming claims. It can say that scientists are just behaving wrongly and they should change their standards. So, there's a lot of controversy about that matter. So, a second argument for accommodationism is the superiority over rivals argument. This is the claim that novel predictions cannot show that a theory is superior to its rivals, whereas accommodations can. So let's take an example to see what this means. So consider Einstein's accommodation of the precession of Mercury's perihelion. Prior to Einstein's theory, this fact was simply an anomaly. No other theory could explain it. And the anomaly had been known for a long time, so there'd been ample opportunity to accommodate it within a theory, but none of the hypotheses about it seemed plausible. The standard hypothesis was that there must be some other planet closer to the Sun, which was called Vulcan, and the thought was that the gravitational interaction between Vulcan and Mercury was what was causing the divergence from its predicted orbit. But then numerous attempts to find this planet had come up short. It was also suggested that there might be a ring of smaller objects around the sun. Again, none were found. It was suggested that maybe the gravitational constant might change close to the sun. That seemed very ad hoc. So there'd been decades of attempts to make Newtonian mechanics accurately accommodate Mercury's perihelion, and it'd just been a history of failure. So Einstein's successful accommodation of the precession of Mercury's perihelion was therefore immediately impressive, because Einstein's theory was the only theory that could adequately explain Mercury's orbit. And as such, it prompted the rejection of all the other theories. So that, as a result, led to confirmation of Einstein's theory. Einstein's theory was confirmed by elimination of alternatives. Since general relativity, did a good job where all of the other theories had failed to work, general relativity eliminated them and thereby achieved very great confirmation. So compare this situation to Einstein's novel prediction of the value of the gravitational deflection of light. Well, this was something that was new and surprising, and as such it did draw a lot of popular attention to the theory. But since it was a new phenomenon, other theories hadn't been examined on terms of how they related to it. It wasn't known whether rival theories might also entail this phenomenon, or at least might be altered in plausible ways so as to entail it. The novel prediction of the value for light bending had much less power to eliminate alternatives. So the assumption here is that scientists respect, or at least they should respect, a kind of equal opportunity requirement. They should give rival theories the opportunity to explain surprising data. And only after theories have failed can the data lend significant support to some other theory. So yes, as the years went by and other theories failed to accommodate light bending, Einstein's theory seemed increasingly powerful. But in making a novel prediction, a theory is not going to eliminate its rivals. Recall Popper's emphasis on severe tests, right? For the accommodationist, what matters is not so much the prediction, it's that you have a theory that has the resources to explain something that's highly anomalous to other theories. The precession of Mercury's perihelion was a severe test for any theory, even as an accommodation. The fact that so many theories had been built to accommodate it and had failed shows this. It's not easy to accommodate phenomena properly. Third argument is the reliability of data argument. This is suggested by David Harker in his article on the predilection for predictions. He points out that the most striking cases of novel predictions are those that have not yet been observed or not yet been established properly. But what this means is that when a novel prediction is shown to be correct, the data is often rather shaky. When a scientist claims to have found a new, surprising phenomenon, it's often possible to question whether the experimental apparatus had been set up correctly, whether the correct statistical analysis had been applied, and so on. So returning to general relativity, everybody knew that the precession of Mercury's perihelion to a very high degree of accuracy because it had been studied for decades. But the eclipse photographs that confirmed the value for the gravitational deflection of light were open to question. And in fact, at the time, there were eclipse expeditions that generated results that initially appeared to refute the prediction. And although those results were, discounted at the time, it was still more open to question than was the value for the precession of Mercury's perihelion. So when a theory makes a novel prediction that fails, the failure can be dismissed by questioning the data. That's not so easy for accommodation, because the data will often have been very, very well established. So there's a sense in which accommodation is in fact riskier. I'm not sure this is such a persuasive argument. I think the predictivist could argue that it's somewhat beside the point. After all, it's certainly conceivable that a novel prediction of new evidence could be just as well established as a piece of old evidence. And even if at first the confirmation of a novel prediction is unclear, over time and with further observation, we gain greater confidence in the data. Really the question for the predictivism debate is, other things being equal, So assuming the piece of evidence is equally well established in either case, is it better for it to be a novel prediction? So I think the reliability of data is, maybe missing the point in this context. Okay, and I guess this point actually brings us on to a final way to argue for accommodationism, which is to explain away the value of novel prediction in other terms. So the accommodationist can grant that novel predictions are generally worth seeking and that theories that make novel predictions tend to be better, but this is because novel predictions are associated with other virtues, not because novel prediction in itself is better. Again, David Harker on the predilection for predictions makes this argument. He suggests that what we really want are theories that explain more and assume less. In other words, we want strength and simplicity. A theory needs to account for a wide range of phenomena on the basis of the fewest possible laws and principles. It needs to be, simple. Newtonian mechanics is a classic example because it applies to phenomena as diverse as the orbits of the planets, falling objects, a swinging pendulum, and so on, and yet it's built on just a few very simple laws. Now, so the thought is then, when making a theory accommodate the data, scientists will often appeal to ad hoc hypotheses, which makes the theory more complex and thereby decreases its virtue, decreases its simplicity. As we saw, this is presumably what happened to Newtonian mechanics with the precession of Mercury's perihelion. In order to accommodate that data, scientists had to make all sorts of ad hoc adjustments to the Newtonian theory. And so they thereby decrease the simplicity of the theory. But notice that ad hoc adjustments like this will not have happened with novel predictions. By definition, a theory could not have been constructed simply to entail a novel prediction. We know that when a theory makes a correct novel prediction, it explains the predicted phenomenon using the same principles and strategies used in the explanation of other phenomena. That's not necessarily the case for accommodation. So the accommodationist can grant that in general it's reasonable to expect that T will be better confirmed if it predicts E than if it accommodates E. But this is because in the former case, when T makes the novel prediction E, there's reason to expect that T will provide a more unified or simpler explanation of the data. It's not that novelty of prediction is in itself of value, it's just that you know that a novel prediction will not have involved a kind of ad hoc adjustment of the theory, whereas accommodation may have. So Harker notes as well that even if novel prediction is reliably indicative of other virtues like this, so are many other things, like the longevity of a theory, the degree of support of the theory among scientists, the reputation of the author of the theory, the publication of the theory in a reputable journal, etc. Obviously, none of these things provide greater confirmation to a theory. If a theory has been published in a reputable journal, yes, like for laypersons, that may be better reason to trust the theory, but it doesn't provide greater confirmation to the theory. Certainly philosophers don't tend to focus too much on these factors, even though Harker suggests factors like this may be just as reliable at tracking epistemic virtues like strength and simplicity as novel prediction is. So the thought here is, well, yes, novel predictions are important, but they're important because they are associated with other things that really matter, not because they matter in themselves. So that was novel prediction. I hope that was helpful, and that's all for today. Goodbye.